Okay, so now we're going to talk about acidic strength. So, what is the main characteristic of an acid? It is the tendency to give the H plus ion, right? So, first of all, the more the electronegative, the more it will develop a delta positive and delta minus here. So, and this is called kinetic acidity. And here we check for stability, which is called thermodynamic acidity. So the more the electron negativity is, the more it will pull, right? So here you have K1, K2, so K1 by K2 is equal to Ka, which is inversely proportional to pK. So if acidity increases, Ka increases, pK decreases. That's important if they ask in the question. Okay. Let's look at some examples here. For example, we have HF, HOCl, HN, IN. Okay, so here electron negativity is good, but the dispersion, which is the stability of the A minus here, which is also known stability of carbon anion or any anion, we check with the dispersion. The more dispersion, the more stable. But here the dispersion is poor. Over here we see it forms H plus, O minus I. Electronegativity is also pretty good here, not as good as HF. And also dispersion is pretty good here. So this is why oxo acids are common. Over here, if it H plus N minus I N. Here, electronegativity is poor, but dispersion is really good. Let's take a look at this for example. H. Right. Now, there's some base. First of all, this would leave forming a plus over here, right? Sorry, minus. And this minus is going to be 6 electrons, which is 4n plus 2 form, which is aromatic. Right. So this H which leaves that forms a stable carbon ion. This is called as acidic hydrogen. Acidic hydrogen. Now they might ask, which is the most acidic hydrogen in a compound? That is the one you let it go first, and then a minus will be formed on the compound. The more the stable the minus, the more the better the acidic hydrogen it is. Okay. Now, how do we compare acidic strength? Let's take an example. Let's say you have HA and you have HB. So first you remove H plus, so you have A minus, B minus. Right. Now there's two cases over here. So it's either negative on same atom, negative on different atoms. For different atoms, there's two factors, which is size, that we check if it's in group, and electron negativity, which you check in period. So the bigger the size, more acidic. More the electronegativity, more acidic. Now, if it's on identical atom or same atom, we have to check the stability. So it's either going to be plus minus I effect or resonance, where resonance is obviously more. Let's take some examples. Let's say HF, HCl, HBr, HI. Now we're moving down a group, so the bigger the better. Okay. Now if you look at across the period, electronegativity we check, right? Just like that. Now let's look into an example which takes carbons. You have this. So you have OET here, O, OET, OET. Now, this is an acidic hydrogen, so let's say minus here. Over here, obviously can go here or here. So, 2 full conjugations possible. See, this one can go here and here, but this also can do resonance here, right? Also 1 partial, 1 full. Over here is 2 partial. So obviously it's this, then this. Okay, next example, let's take this. So you have fluorine here, then you have O minus, OH, right? This leaves O minus you get. O minus Cl. Now obviously this O minus here can rotate and it can come over here minus, or it can come over here minus. This and this can do d orbital resonance, Cl, and it has d orbital. So this is important. Next we check something called hydrogen bonding. Let's take for phenol case. What is phenol? It's benzene with an alcohol group. Let's take NO2 here. So this is here. It's in hydrogen bond. That means it doesn't want this H to leave. It has to overcome the hydrogen bonding. So this is why it is less acidic than OH, let's say in para, because it's a hydrogen bond. But for benzoic acid, let's say you have this. Let's check here. There's a bulky group. This bulky group will make it more acidic because it'll stop the resonance in COH, right? With the ring, right? With the ring. That's why it's making it more acidic. Makes it more acidic. And hydrogen bonding also supports this, right? But not in phenol. So let's take some case in benzoic acid, COOH, NO2, Br, chlorine, OH, OMe. But if we have COOH, OH, OH here, this is more than all of these, right? Okay, that's enough for acidic strength. Next video we'll be doing basic strength. Thank you.